Welcome, everyone, and thank you for joining us today. My name is Paul Donahue, and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end, and we'll certainly follow up with any unanswered questions via email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components. We talk about some of the related technologies and certainly the extra design and engineering value that is added by a custom manufacturer such as Quantic TRM. To begin today's session, I am once again pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and numerous white papers and technical articles on passive microwave technology, Shaun has been with Quantic TRM since the late 90s, and his passion for the job and for solving customer problems has only increased over the years, especially when it comes to resolving some of the unique design and engineering challenges that customers have. So welcome, Shaun. Can you share an overview of today's topic and your objectives for the session?
Yeah, thank you, Paul. So what I'd like to talk about today really is, as the topic indicates, this is what a power divider is. So we're going to start by basically going through what is a power divider, and really why do you need a specific device to do this. We'll go through the different classes or different types of power dividers. As we're going through there, we'll talk about the strengths and limitations of each type. Like any technology, each approach will have strengths and weaknesses. We'll go through a quick summary, and then we'll go through some Quantic TRM differentiators.
Okay, well, that sounds good. So to get started, what is the best definition of a power divider?
All right, so power dividers are really a device that can equally distribute RF energy or unequally distribute, depending on how the design is, to various portions of the circuit. It's passive in nature, so therefore power is simply divided, as the name implies, as part of that distribution. So as a result, since it's purely passive, that from a power standpoint, if you have a two-way power divider, you're going to get half the power being distributed out to each of the 2 outputs. That's 3 dB. If you have a 4-way, it's going to be divided by 4, in which case that's 6 dB down. And for an 8-way, that's 9 dB down. In addition to that, there's also some non-recoverable ohmic losses that do happen within these devices. So there's always a little bit more that you have to plan on. The other thing also that's important about a power divider, and this is really what makes it a device that is useful, is that all the ports are at 50 ohms, so that regardless of which port you go into, you will get a 50 ohm match. And for most of the designs that we have for this sort of device, there is isolation between the output ports, which means that any signal that gets reflected back won't be shared among all the other devices that the signal is being distributed across. So that isolation helps with a lot of system performance sort of requirements.
Well, that sounds good. And why is it, Shaun, that all ports need to have the same impedance?
Yeah, so this is actually where the power divider really becomes a device that needs to be specially designed. If you just took 3 wires and put them together, yes, you would get a power divider of sorts. That's how power works in your house, right? You take wires and you tie them all in parallel, and you end up with distributing signals out. What happens when you do this, though, if you think about a simple Ohm's law case where 2 outputs are at 50 ohms, if you put 2 50 ohms resistors in parallel, you're going to get 25 ohms. Well, 25 ohms to an RF circuit means that you now have a VSWR of 2 to 1, or a significant reflection that is now going to happen with the energy, and the energy transfer to those 2 outputs is going to be degraded significantly. So in an RF standpoint, we want to make sure that all of the ports are matched to 50 ohms. Well, in order to do this, you have to have some sort of way of, I'm going to say, magically transforming the impedance of the outputs of 50 ohms up to 100 ohms in the two-way case, so that when you do put them in parallel again, you end up with a 50 ohm on the input again. So this impedance transformation is something that really needs to be done within the circuit, and that is the nature of the RF power divider. Is it's really an impedance translation device that when you do make all the combined impedances, you end up with 50 ohms on every port. And there's lots of ways to accomplish this.
Okay. Now, you mentioned earlier that there are different types of power dividers. Can you share an example?
Sure. The simplest one to go through this is something called a resistive power divider. And what this does is it puts a resistor in series with the line. So therefore, I'm taking my output impedance of 50 ohms. I'm putting a 50 ohm resistor in series with it, and therefore, when I do put those in parallel again, I come back down to 50 ohms. So this over here is the simplest case. Now, the beauty of this is that it is theoretically very broadbanded. This is essentially by design, this is an what we call an all-pass network, which means that it will have this impedance transformation across all frequencies. The downside of this, though, is this will have twice the insertion loss as the split loss. Therefore, for a two-way resistive power divider, you're going to have 6 dB worth of insertion loss through it. And because, as you can notice by the graphic in the upper right-hand corner of your screen, this is a symmetrical device. And by having it be symmetrical means that there is no additional isolation between the output ports. So the isolation on the output ports will be equal to the insertion loss going back to the common port. From a strength standpoint, this is a very broadband network. It's very easy to build, and it can work pretty well. The weaknesses of this device over here is that because there is so much insertion loss in it, for any kind of significant amount of power, we're going to be generating a lot of heat in those resistors. In addition to that, from a weakness standpoint, there is very poor isolation or essentially no isolation between the two outputs. Therefore, energy that goes into any one port will appear at the other two ports and at the same value. Therefore, there really is no isolation going on between these ports. A very useful device. Said it's simple, very broadband. It does have a lot of insertion loss, though, twice what a reactive power divider would have, and there's no isolation.
Well, I've also heard you speak of a lumped element power divider. Can you explain more about the pluses and minuses of that?
Sure. So the lumped element power divider is the first of a series of power dividers where we're using transformers to change the impedance. As you may know, you can use a transformer to do a number of jobs in circuits, whether it's increasing voltage, decreasing voltage. You can also use it as an impedance translation device. And that's what we're doing here for a lumped element power divider. Here you can see in that schematic that's up on the upper right-hand corner, you have the two outputs. They're going back into a center tap transformer. That brings the impedance, if the two outputs are at 50 ohms, at that central node, that impedance is now 25 ohms. I then use a 2-to-1 impedance transformer on the input to bring that back up to 50 ohms. So since this is a wire wound lumped element sort of device, theoretically, this is a high pass structure, meaning that the low end is set by the inductance of the transformers, and therefore it will work as a impedance transformer for all frequencies above there. However, being practical, there is an upper limit to this based on the parasitic inductances and reactances that happen between the wires and the ferrite core as this is built. So as a result, these typically run to about 100-to-1 bandwidth, which is very broadband. The frequency is set really by the amount of inductance that you can build into the transformers. And it does a very good job of having this impedance transformation working over a very broad band. These parts, since they are lumped element devices, are very compact. You can build very low frequency parts here. These are really effective from frequencies down to kilohertz, right on up through about 2 gigahertz. So basically, these are used from HF through L-band, and this is a very high performing sort of device across that bandwidth. The sort of downside of this sort of device is clearly that the upper limit from a frequency standpoint is still fairly low. You have to be below S-band in order for the sort of device really to operate efficiently. And because wire wound transformers and ferrite cores do not do a very good job of dissipating heat, you do have, if you're running these at higher power levels, you do have to have special thermal management and air movement to get the heat away from the cores, as this is for higher power applications. So some special consideration needs to be done if you're going to be running higher power through these devices. In addition to that, the higher power that you're going to run through these, the larger the core needs to be, and therefore the parasitics increase and the bandwidth decreases. So a very high power ferrite-based device will have much lower bandwidth than 100 to 1. A low power device can go up to about 100 to 1. So again, this is really a fantastic circuit for lower frequency type of operations. It's efficient. As long as the power levels aren't too high, you can get very good bandwidths out of it with some good compact and good high performance. This does also provide isolation between the outputs. So this is a really an ideal case for lower frequency operation.
So it seems there are clear differences in when you would want to use one type versus the other.
Yes, absolutely.
What about the Wilkinson power divider? What's special about that?
So the Wilkinson power divider does another way of doing the impedance transformation. The simple two-way case, single section that's on the screen, you can build an impedance transformer by simply using a quarter wavelength line that is in an impedance other than 50 ohms. In this case over here, a 70.7 ohm line that is a quarter wave long will transform the 50 ohm output impedance back up to 100 ohms. Again, this will give you the impedance transformation to maintain the requirement for a 50 ohm impedance on all three ports. This over here, like I said, this is a very good structure, really for, I want to say, probably UHF and up. This over here, and that's really mainly due to size. If we want to build a broader band sort of Wilkinson than the single section is good for, a 20-30% bandwidth. You start putting two sections onto it, you can get an octave. And by increasing the number of distributed transformer sections, being practical, you can get about a 10 to 1 bandwidth out of this sort of structure if you were to go in there and have, say, eight or nine sections cascaded. This really works well for higher frequency operations just due to the size. Each one of these transformer sections needs to be a quarter wave long. Therefore, with the lower frequency, size just becomes impractical going through there. This really does a very good job as a power divider, driving higher power levels, because really the only loss that you have in this circuit is the ohmic loss of the copper, as well as the losses in the dielectric itself. So therefore, it can be quite efficient as a power divider for fairly high frequency sort of components. This can be built in either microstrip or strip line. And really, it's again, a very high performing unit for a little higher frequency sort of devices. The one downside of the Wilkinson style power divider is that when you go to use it in the combining mode, the power dissipation in the isolation resistor really isn't very good because of the thermal path that you have to have, since it's mounted directly between two nodes in a balanced configuration. Heat transfer out of that sort of configuration usually isn't really very good, and therefore it does have limitations as using it as a broadband power, high power combiner. Low power combiner works fantastic. Truly, when you get to higher powers, you have to be careful with that. And then there are other topologies that we'll use, and we'll talk about more of that in the future. as far as how we have higher power combiners and how we deal with that heat issue with those devices.
Well, okay. Now, are there any additional types of power dividers you might want to discuss today?
Yeah, absolutely. So getting a version of the Wilkinson, again, this is another distributed sort of transmission line, is to use a tapered line. This over here now, you can design these as being high pass structures as opposed to being band pass structures like the Wilkinson. Wilkinson dividers are always designed as band pass structures. Tapered lines can be designed as high pass structures, and therefore, as long as you can suppress higher order modes in the microstrip or strip line, these units will work over extremely wide bandwidths. And really, the limit is the mechanics of how you do that. Mathematically, these will work so that they're pure high pass structures. Therefore, you can get really broadband sort of performance out of these. A lot of the other advantages of the Wilkinson are still here. The main difference here is this is a high pass structure rather than a band pass structure. You can very easily get 3640 to 1 bandwidths out of this sort of structure. The kind of downfall here is that these structures tend to be fairly large, depending on how low in frequency you want them to operate at. These have to be, in excess of a half wave at the low frequency cutoff, and therefore they tend to be quite long if you want to go very broad band, going down to low frequency. The one that's on the screen, for example, that one there is one that Quantic TRM designed that works from 0.5 to 18 gigahertz. You can see how long it is, and with that much line at 18 gigahertz, there will be some insertion loss just due to ohmic losses. Other than that, the part works very well over very broad frequencies. If you were to build this, for example, to go up into Ka band, then you bring the low frequency cutoff much lower. You can then shorten it up significantly, and then have a good high performance, high frequency sort of power divider.
Well, good information, Shaun, as usual. Would you like to summarize?
Yeah, sure. So what we have really are really the one key concept is that power dividers are really impedance transformation devices so that we can make sure that all the ports have good VSWR. This is critical, and it's a key item for what power dividers really do for a living. To accomplish this, I talked about 4 different types today. The resistive power divider, which has very broad bandwidth performance. Again, this is a theoretical all-pass network. It does have twice the insertion loss as the other types of dividers, and it does not really offer any kind of isolation between your output ports. The lumped element devices are high-pass sort of structures, limited on the high end by the stray reactances that we get off of the transformers, which really limits this technology down something below S-band. Although below S-band, these are they're very size efficient, and they do a very good job with what they do. The Wilkinson power divider is the next class up in frequency. These are really efficient, really starting from UHF L band and up. From a structure standpoint, these are band pass structures, and therefore the more bandwidth, the more sections that you need to add, and the higher the insertion loss that you get. These are very good power dividers for, like I said, up through 500 megahertz, a gigahertz up, and you get some very good performance out of it. Again, these are usually built in microstrip or strip line. The tapered line power dividers is the last one that I discussed. These are high pass structures, and you get very broad bandwidths out of these. Like the Wilkinson power divider, the more bandwidth that you're shooting for, or what the lowest frequency actually is, that ohmic loss going up to the high end of the band can become significant, and they become physically very large to be able to accommodate that broad bandwidth. But from a manufacturing standpoint, again, these are usually done in either microstrip or strip line.
Well, okay. And what are some of the ways in which Quantic TRM differentiates itself in this area?
Yeah, so really what we do is we like to work with our customers to find out really what your needs are, And just from the topic today, if you're looking for a power divider, there's a lot of things to talk about here. What is the power level? How much insertion loss can you actually work with? What sort of bandwidth do you really need? And going, some people will go in there and offer, for example, if I can get more bandwidth, it must be better. Well, the more bandwidth usually comes at a cost, and it's usually insertion loss or reduced isolation or reduced amplitude tracking or any other parameter. So it's a matter of understanding really what it is that's important to you in your circuit to make sure that what you get is the best topology and therefore give you the best performance for what it is that you're looking for. As we're going through this, we look at materials, approaches, and of course with the mechanical packaging is just another piece that we really focus on to make sure that the device meets your needs. Sometimes your needs is also things like data. We're happy to supply testing and objective evidence that our devices do meet the full parameters across all the environments that you're going to be working over. And I'd like you to think of TRM as really being a solution provider for these sorts of devices.
So it's just not components. There's a whole other end to it.
Exactly.
And I think we have time for one question, and maybe this aligns with that concept. But if these that you've discussed are more or less different standard types of power dividers, what is it that might be different about those that, as a custom manufacturer, Quantic TRM would provide? What do you add to those that are custom made?
Well, and I think that kind of just traces on the previous comment, Paul. What we have really are what we will do is we will work with you to find out exactly what it is that's important to you, and from there pick the topology that is best suited for that application. There are, for example, certain frequency bands where you can build this virtually any way that you want, especially if you're working, for example, like an L band. You can build that as a Wilkinson power divider. You can have a broader frequency tapered line. You can build that as a lumped element, or you can build it as a resistive power divider. Really based on your application and what parameters are important to you, whether it's a straight swap analysis going through there and figuring out whether size is important, whether weight is important, or whether power is important. We can go ahead and do that trade-off for you to make sure that what you get is the optimum part for your specific application.
Well, that makes good sense. And I think in conclusion, the bullets on the screen here, I think, say it all and summarize what you've just talked about. Going forward, our next Tech Talk will be on Tuesday, March 26th, and the topic will be Power Combiners 2.0. So, Shaun, thank you once again, and thanks to all of you again for joining us.
Thank you.